Good afternoon, everybody. Welcome back to lecture number
31.
31. We are in week 11, okay? We are in week 11. Okay? So, we will continue our example. So, note that now we are at revision 4. Revision 4 of the DC control, okay? So we will get, I think, every lecture a revision because I'm adding the slides slowly as we speak. Do you remember the difference between K flux in voltage second per radians versus the voltage over RPM? Those two different constants, because they are measured in different units. So this is one of the examples, I think example 3, solves directly EA equals K RPM N. So if you put N, you use the constant P over RPM, or you convert this N to omega and use this constant. Okay? Another thing is, if you change the flux, will K change or K times the flux change? Think. What is K? I think we call it KA. KA is a function of the machine itself, the windings, the cables. But K times the flux is a function of the machine times the flux. So if you change IF, this constant will also change. So do not be tricked by thinking that this is always a constant number if we change the flux. So you can change this constant if you change the flux. So anytime the flux changes, for example, if you change RF, it will change. Clear? This is very important. This is a constant, but don't say it's a constant and maintain it for different IFs. It is a constant because we're assuming the flux is constant. If you change the flux in the two different speeds, or two different N's or omegas, then K times the flux, whether it's in voltage second over radian or voltage over RPM, it will change. We will see an example today. Clear? Is it clear? So, do you remember our favorite operation for DC control? Up until the base speed, we do what? Change the voltage. Increase the voltage linearly. We're going to maintain the torque. Above the rated speed, we enter field weakening, where we control an IF control. If we enter an IF control, this KA times the flux will change. If we are below omega speed at the V control, this constant is fixed. Okay? So that's very important. So let's continue the previous example. I think in the previous example, we calculated, we had series motor with a fan load. So series motor doesn't have this equation because it doesn't have a field. Series motor has different equation, which is torque equal KSR times IA squared. So what we did here is we calculated EA from VT minus IA times the three resistances, and I told you RAA is the control one, and it's 0 before you start, according to the problem here. No external resistance, so RAA is 0. It is 195. You assume, you calculate the power, which is EA times IA. IA is given in the problem. Where is it? So 25 amps. So it is 4.8 kilowatts. From the power, you get the torque divided by omega operated, which is, I think, 300 RPM. So convert 300 to 2 pi over 60, it's 155.2 Newton meter. This is part A. Part B, you have to calculate the constant KSR. So one way to calculate it is through the torque. So torque over Ia squared is 0.248. Now, if you change the motor speed, will KSR change? No. The torque will change. So the torque is according to this equation. Where is it? If you go back to the series motor slide. So make sure to understand these equations. Where is it? So this is the equation EA equal KSR times IA times omega M. So if you change the why do we have square? Do you remember why we had square?
It was fan load.
Okay, because it's fan load, thank you. Because it was a fan load, because it's a fan load is now, the speed is to be reduced to 200 RPM, you're right, thank you. So the T load, it is K of the fan times omega squared. So we have two different torques, so divide by TL nu over the constant of the fan over omega nu squared. So that's why the ratio is proportional. So the new torque is new speed, which is 200 times 2 pi over 60 over 300 times 2 pi over 60. They will cancel. Squared. The K's will cancel. That's why we had this equation. Times the old torque, which is 155. So the new torque is 69. Get the new IA. You have KSR. You have the new torque. It is 16.68 amp. Okay? Now to calculate EA, you use the equation KSR times IA times omega M. You already have this equation. You can get a new EA, which is 86.57. You can substitute in this equation and calculate RA needed to achieve 86.57. Solve it and you should get 7 amp. And here we can confirm that we are getting a new quantity of power, which is 1.4. Does it make sense if you reduce the speed? You reduce the power? Yes, because you reduce the torque. It's a fan. It's a fan load. Thank you, Mr. Nawaf, for catching this. So the key word here is fan. Always the fan is K of the fan times omega squared. That's the model of the fan. Same as the project. Did you start the project?
Not yet.
So you have to do the project, okay? It's more important than the senior project.
The deadline for it?
15 or 16 May. But still, you have time. So let's see example number 5. Example number 5, we have a shunt motor, shunt DC motor, where we have RA, we have RF. So we have RA 0.25 ohm. We have RF to be what? 120. And then we have IA full load. At full load is what? 40. And full load is what? 100 RPM, okay? Find the developed torque. It's easy. It's a shunt. So EA is what? VT minus IARA. You already have the VT. It's 240 minus 40 times rubber. Ashara, it's 230. Is it correct? 230. So what is the omega? 2 pi over 60 from physics 101 or 102, I think 101. Angular speed times N full load is going to equal to 115.192 radians per second. So what is the developed torque? Get the power. EA, IA, this is developed P or PD or PDEV as long as you know what quantity you're talking about, it's not the input power, it is the power that is across the brushes of the motor, the armature. You will calculate it to be 9.2 kilowatts. So what's the torque? 9.2 kilowatts divided by 115.192 radians per second, and you should get the torque to be, I don't know, 79.9. Okay? So now this is from EE360. Find the, I think in EE360 they even used to ask such questions. Change the field. So find the new operating speed if armature current remains constant. So here we change the field current, but we are fixing by some control the armature current. For some reason, for some assumption, maybe you have a current limiter, like in the project. In the project we have what? Current limiter. Remember a current limiter, there is a maximum limit for the current that the motor draws. That's the purpose of a current limiter from its name. So if you do this, you have to get a new IF. What is a new IF? Let me ask you a question. What region are we operating at? Find the new operating speed. So this is alpha mia. If you change RF to be smaller, 150, what is IF? It's going to be bigger.
Yes.
So what will happen to the flux Ka? It will be bigger. What will happen to Ea? It will be bigger. What will happen to the developed power?
Bigger.
It will be bigger. What will happen to the torque?
Also bigger.
It will be bigger. So what will happen to the speed?
So,
Let's check. No, not the torque will be smaller. So the power will be bigger, but the speed will be larger. So EA actually is fixed here. No, EA1. No, that's not the right way to do it. So get the field current, it will be smaller. So EA, why did he say, oh, because the armature current is the same. Because the armature current is the same, both EAs are the same. The armature current is still 40. Because this is very important assumption. The armature currents remains the same. This means that the generated EMF remains the same. That makes sense because VT has to be 250. So IA, RA has to be fixed. So EA must be fixed. Okay? So that's because of this assumption. If this assumption is not valid, then we will solve it using the method I just explained. Okay? If the armature current is not the same, if it's allowed to change, what will happen is we will go through the flux route. EA equal KA times the flux. But because EA is fixed, KF times IF times omega 1 equal to KA times IF2 omega 2. Or you can use K times the flux, and you can say the flux have a ratio of 2 over 1.6. You can solve it this way. So the new speed is 1375 RPM. Clear? Okay?
Doctor,
Yes.
the torque will be lower, correct?
No, the torque will be the same.
The same. So we overall will have.
No, the torque, no, the torque will be lower because EA times A is fixed. EAIA is fixed. So omega is up, torque will be lower. You're right.
So we are not increasing the amount of power that much.
No. That's the purpose of this assumption. The drawn current is fixed.
Right.
If the drawn current is not fixed, you have to use this TA times the flux. You have to have a new EA. Because a new EA will be higher, you have to go through another equations, okay? They have to tell you what will happen to the torque or speed, one of them. They cannot tell you, I cannot give you a problem without telling you what will happen to the torque and the speed if I don't fix the IA. Fixing IA means fixing the power. Clear?
Yeah.
So is example 5 clear? Let's do example number 6. Make sure to solve these examples. We started solving them since yesterday. Not yesterday, Thursday.
Victor, measure to material.
Material, where is the meter?
Upper part.
14. So until this material. But here on 14 we will have online lecture review. The help session. Okay? Clear? And then we will have the trip. So we need to substitute the lecture of the trip. Because he's not going. He's not going.
I will go.
Ramlas is not going. Where is your name? Masjid? So if you're not going to the trip, we have to have a substitute lecture.
دكتور هذه الريبتيشن ما يكون بنفسه الميجر قبل
عندي.
Material is too small.
I know.
The reason is because I will finish writing it maybe that day. I can give you hints. But it's up to you. You want to have it before? When double? Okay, let's coordinate by email. Maybe we will have it 13 at night. Okay? And then we will not have a lecture. 14. Okay? Attendance will be taken. Let's continue. So you decide, and then we can decide next week, okay? It's not. ما راح نختلف. Variable speed drive. What is variable speed drive? Power electronics. Variable speed drive is somehow a power electronics. Uses separately DC excited motor that is supplied from variable voltage source. So a variable speed drive uses separately excited DC machine. The torque and power profiles are shown in the figure below. So he's telling you we're doing constant torque, constant power operations until we reach omega speed. The drive speed, so this is a drive. So basically drive is power electronics plus your separately excited DC motors. It is capable of driving another machine, like two machines connected together. So that DC motor, maybe the variable speed drive would drive a generator, for example, like E360 or the machine's experiment. From 0 to 15 RPM, we vary the voltage from 0 to 500. And we maintain the field. Find the motor armature current if the torque is held constant at 300 Newton meters. So this torque held constant 300 Newton meter. Find IA. So how to solve this equation is we have in base is what? Don't use capital, use small. 1500 RPM. Now, did he tell you what is IA?
No.
So that you can use the equation VT minus IA RA equal EA. How many unknowns? EA, IA, two unknowns. And as a matter of fact, he's asking for IA. So do I know EA? Not really. So can I make an assumption? Say, okay, let us estimate EA roughly speaking, equal to Vt, because there is no other way. Usually, what is IARA? Maybe 2 volts. Who cares about 2 volts? So we try to find EA equal KA times the flux, and he's using the, I think he's using this constant. So now I'm going to use the RPM constant, because we have the speed in RPM. So if you solve it, no. This is the equation. K flux. No, he's not using the RPM, he's using the omega. That's fine. Omega base. So what is Ka times the flux? Is Ea over 2 pi over 60 times 1500. So what is Ea? Is Vt, which is what? 500. So 500 over 2 pi over 60 times alpha comes. Mia, you get, what's the value of that constant? 3.183. What's the unit? Volts times second over radians. Okay? Now let's use the other equations. Go back to the equations, the separately excited. Don't we have this equation? So what we use this equation. We estimated Vt equal IARA to be, roughly speaking, Vt equal to Ea. So we found the constant. So this constant is estimated, so I can use it from the torque. 300 over this constant will give me Ia. So Ia is torque over Ka times the flux. This is in voltage seconds over radians. And you should find example 6 to be 94.227. Now, I forgot to mention one important thing is you see this red box, neglect all losses. In the question, he said neglect all losses. So one of the losses you can neglect is rotational losses, which includes IARA at no load. So you can estimate Vt to be equal to Ea because of this statement, neglect all losses. The speed beyond, okay, so now we found Ia. Part B, the speed beyond the base speed is obtained by field weakening. While the armature voltage is held constant, so Ea is assumed to be constant, find the torque available at speed 3000 RPM. So the torque will be smaller based on the curve. If the armature current is held constant at the value obtained. So Ia is now fixed. Clearly here we use the equations the same. So start with, now let me ask you the question, will the constant stay the same now? Will Ka times flux be the same or different?
Different?
It will be different. So we repeat the same method. Ka times the flux at a new speed of 3000 RPM is what? 500 over 3000. So this constant will be smaller. 1 point, it's field weakening, so the field becomes smaller. So the field weakening constant, the Ka times flux, is now 1.6. What's the unit? Voltage times seconds over radians. Again, we're not using the RPM, we're using the one in radians. But because we changed the flux now is changed, okay? So again, you repeat the same story for the torque. You already know the omega. Here the power is fixed, 500 times IA, 94. IA is the same. So the power is EA times IA. Power is fixed. And you can see here even power is fixed from the omega base. From the omega base, it's fixed. So I think this example is a nice one, okay? Any question about this example? Clear? 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 Now, to save time, because if you have any question while you're studying that you do not understand, contact me by Teams. I'll try to answer, okay? If you don't understand how did we jump from this step to the other, of course you have to watch YouTube. You have to watch YouTube, okay? Now, solid state converters used in speed control of DC motor. The purpose of this slide is to introduce you to different types of configuration. So is this one similar to the project? No? No, it's different. The project we feed omega 2 times back to a omega command, speed command. Here we take the current, we measure it, we multiply it by a constant, we put it to a current limiter, we take the cosine inverse, we get the firing angle, we apply to power electronics. We don't have power electronics. We have current limiter, but we do not have power electronics in the project. So this is another way or another system to apply the control. And actually this stems from, you're familiar with this. This is the motor model. You're familiar with it, صح? We already explained it. This is the motor model. If you put it inside this box in Simulink, if you double click, you will see this box. Here we have beta, not to be 0. You apply a PID controller with a reference voltage. So the PID controller here is after the voltage. So one way to apply it, it's not in series. Mr. Murtada, you're not happy looking at this? IA is fed back to the PID controller. So you can look at the whole setup. This thing in blue is actually the PID controller. You see it? P is derivative, I is integral, no, P is proportional, I is integral, D is derivative. So this is a PID controller because you're taking the current, taking some information. Sometimes you take the speed, sometimes you take the current, feed it back to a complex system to satisfy the control over a reference voltage. It doesn't matter if you control the reference voltage or you control the reference voltage minus the voltage feedback. Everything is fed back. But this is one topology. There is tens of topologies. The other topology I wanted to show is the one in the project to control. Okay? So make sure to understand from looking at the block diagram what your system is doing. Okay? Okay? So if the supply is AC, the control rectifier can be used to convert fixed AC supply voltage into variable voltage to DC supply. So this is what we mean here, for example. If you don't have DC, which most likely the case, we only have AC, your only way is to get converted to a variable DC source. So one way to do that is by applying power electronics. Okay? One way to do it is to apply power electronics. How we do this? If you have a single phase, for example, this supplies single phase, you apply the power electronics. I am not going to ask you questions about the figures, but I'm going to ask you questions about maybe the circuit itself, the topology. I'm not going to ask you about draw a figure, but understand how it works. Please focus with me. We already explained it before. What is this equation? This equation is the average DC that you get it by a firing angle alpha from a supply phase voltage. You apply AC, you make switch 1 and switch 2 on. So this is on, this is on. How do you make it on? This is power electronics or industrial electronics. While the anode is higher than the cathode and the pulse at the gate is active, this will conduct. So at positive cycles, the anode is higher than the cathode. At positive cycle, the anode is higher than the cathode because the cathode here is more negative. Send a pulse here, send a pulse here, it will conduct. We have L, we have R. L would not, DIdt across an inductor. The current cannot jump across the inductor. So this would limit the current burst to be smooth. Apply this at an alpha, for example, 45 degrees. So at alpha 45 degrees is here. Alpha 45 degree is here. This is 45, this is 180. So at 45 degree, send the pulse. Send the pulse. If you send the pulse, S1 and S2 are open, you're going to have IO flowing. You're going to have IO flowing across the IO. We're going to have a current flowing because this is closed, current will flow. What is V output? This is V output. V output is not EA, V output is the whole voltage drop here. It will match the AC until it goes to negative. And we send another pulse at pi plus alpha, which is 180 plus 45. We send the other pulse at S4 and S3. And again, we are at the negative half cycle, so the anode is higher than the cathode. This is more negative, so it will satisfy the condition. Anode is higher than the cathode. This is the anode. This is the cathode. So at negative cycle, anode is higher than the cathode. Anode is higher than the cathode. Send a pulse. These two will be on. This will be off. And then pass the negative signal. So you may ask yourself, I am applying the output that's somehow chopped. It's not DC. It's not pure rectified. We look at the average. Because what will happen is at very fast frequencies from the AC supply, you're going to apply a positive DC, roughly, we can say it as DC, and then you apply a small negative. Then huge positive, small negative, small. So what will happen is, because the electrical constant is faster than the mechanical constant, the motor would still rotate clockwise. Okay? This is in a nutshell how it works. You don't have to know the details, but you have to know the equation. And then they estimate the DC voltage by the firing angle. Let's say the firing angle now is at 135. 135 is you fire at a negative. What will happen here is at 135 you would conduct a negative current. 135, you conduct a negative. And then you have small positive. Negative, small positive. So is this, what quadrant is this?
Second quadrant.
No? Remember, we're using torque omega. So torque, is it positive or negative? Positive. Current is negative. We operate at the fourth quadrant. We will talk about braking in the next few lectures, maybe next lecture or the following one. So we are here at what we call regenerative braking. Reverse regenerative braking. So one way to do regenerative braking, Osama, is to have a firing angle that's more than
90.
90 degrees. And now we know how the Teslas work. Without power electronics, without Dr. Mahmoud Qassas, we cannot survive. We cannot. And you can see how DC motor can enter into dynamic braking. How did we enter dynamic braking for induction? You remember? We had to wait until we slow down. But here, for a DC motor, by just changing the firing angle, I can trick the machine to have a negative DC from an AC supply. It doesn't mean it will rotate counterclockwise. It means we are entering a regenerative braking. It means what? It means we are sending power from DC to the supply. And this is one way to think about how regenerative braking sends the power back to the battery or to the supply. Do you see it?
Yes.
Do you see that because here the power is negative, it means this movement of the DC machine would generate the power back to the supply? I'm not going to ask you in the test, but what I want to ask you is similar to the example. 3-phase. Can I do it from 3-phase? If I can do it in single phase, I can do it in 3-phase. How many switches in single phase? 4.
4.
How many switches in 3-phase?
12.
No?
6.
6. S1, S2, S3. So you have to operate, you know what's the sequence of operation.
واحد مع هذا بعدين
1, 2,
5.
3,
1
4.
6 بعدين 1 2 بعدين 3
No, 1, 6. Then 1, 2,
بعدين 3 2
3, 2,
بعدين 3 4 بعدين
3, 4, but then 5, 4, but then 5, 6.
بالضبط.
Okay? So the sequence is fix 1, attach the 2 others. Fix 1, don't connect them the same column. What is the equivalent DC? Is this number 3 times square root of 6 times Vp over pi cosine alpha. And this is the operation, and you can see the signal is more smooth. It doesn't have negative. It's more VAB. And you take VAB or VBC. So sometimes you take from phase A, sometimes you take from phase B, no, AB or BC or CA. And that's the operation. And they are 60 degrees apart. They are what? You don't have to worry about the firing angle. You do not have to worry about the firing angle. Or you can use DC chopper. What is a DC chopper? A DC chopper is nothing but a simple structure. This is the diode for protection. A switch that you only close it 10% of the time or 20% of the time. Then instead of having 120 volt, maybe I have 12 volts if I have 10% duty ratio. So the time it's on over across the total time is alpha V. So if alpha is 0.1, then I have a reduction of the DC. So I chop the DC. This is simpler to operate. Keep in mind IA doesn't change suddenly because of the inductor. Nawaf, why do we have inductor?
So
Why do we have LA?
So it doesn't change suddenly.
Doesn't change suddenly. And we capture it in dynamic, not steady state. And do you use equations or you use Simulink? Simulink. Okay. خلاص. So that's the duty cycle, and that's how IA it works. So let's do a quick example 7. Example 7 is speed of a 10 horsepower 220 volt 1200 RPM. So this is supply, this is rated speed, this is rated power. Separately excited DC motor is controlled by single phase converter. The rated armature current is 40. The armature resistance is this, LA is this. AC supply voltage is 260 volt. So the AC is come 260. The motor is rated at what? 220. So let me ask you a question. Is 265 single phase or 3 phase?
3 phase.
No, he's asking you a single phase. He's telling you
if it's
single phase full converter.
Uh-huh.
So is this line to line?
Yes.
Yes, it's because we love line to line. So convert 265 from line to line to V phase. What is V phase? Divide by square root of 2. So what is VP?
2 or 3, Doctor.
Hmm?
Divide by square root of 3.
No, line to line is only for 3 phase. My bad. Is this RMS or peak? This is single phase, not 3 phase. Line to line is only for 3 phase. Is this RMS? Yes, it is RMS. So that's V phase. It's RMS. So you plug VP here times the equation 2 square root of 2 over pi VP times cosine alpha. What is alpha? 30 degrees. So what is VT is 206. So now we're sending an average value of 206 DC.
So دكتور الفولتج الموجود عندنا هذا بيك ولا رمس؟
RMS. We love line to line. We love RMS for AC. Line to line if it's 3 phase. RMS for all. But it's not peak. But the equation here is not peak. It's V phase. P stands phase. P stands for what?
Phase.
Phase. Not peak. That's the equation. Yeah, V phase. Okay? Watch YouTube and you'll be fine. Now, the question is find the speed of the motor. To find the speed of the motor, I need to find EA. EA is 206.6 minus IARA. It is 196. So 196 divided by the torque. Is it the torque? No. The constant. Ka times the flux, theta, is 0.18 V over RPM. I get the speed in RPM. So I get the speed to be 1092. Remember the equation? EA equal Ka times the flux in RPM times N RPM. So he wants the N. He gave you the constant, you calculated EA, get the N. N is what? 196 over 0.18. And solve it. Okay? The part 2 is find the motor torque. To find the torque, what he's doing is he's getting the constant VRPM, he's converting it to radians per second, and he's using the equation T equal Ka Ia times Ia. This has to be in voltage second over radians. So that's why he did the conversion. The equation حقت التورك, it has to be voltage radians over second. Why? Voltage seconds over radian. Why? Because torque is a rotational quantity. You cannot apply angular speed. So this constant cannot be used for torque equation. To be safe, convert everything to omega and use one constant to be safe. Okay? The last question is find the power of the motor. To find the power of the motor, it's I square RA plus EAIA. So here what we have is we have I square RA losses. We have I square RA losses. Or you can use VTIA. So use VTIA. VT is the DC supply, which is 206 times 40. So you may ignore this equation and just use VTAA, input power. So here the question is find the power to the motor. That the power that draws from the converter is the DC times 40, and it's clear. Okay?
Yes.
For the 3-phase problem, here is another example. And for the duty cycle, there is another example. We'll try to solve them next lecture. Okay? Any question about today's example? Any question? واضح؟ هل هي سهلة الأمثلة هذه؟
وسط.
Okay, go over it. If you have questions, let me know. You have to study them, okay? Do you think we have enough time to do example 8?
دقيقة باقي.
خلاص, let's do it next lecture. Okay? توفيق إن شاء الله.